Hi everyone, a warm welcome to today's webinar. It's a pleasure to have you all join us for an insightful session on the missing link in RAN testing, combining real UE validation and AI-enabled log analysis. I'm Rohina Chapla, and I'll be your host for this session. A few points before we begin. We will share a recording of the webinar with you all to revisit at your convenience and share ahead. Also, we recommend you use headphones for a better experience. Lastly, if you have any questions or clarifications during the session, please park them in the Q&A section and we will take them up at the end. In today's session, we will focus on a topic that's becoming increasingly critical in modern telecom operations, RAN testing. As 5G networks scale and diversify with Open RAN, virtualization, and non-terrestrial networks, the limitations of simulator-only testing are becoming more apparent. Today's discussion will explore why real-world validation using actual user equipment combined with AI-powered analysis is essential to building resilient, reliable, and field-ready RAN infrastructure. To guide us through this critical conversation, I'm pleased to introduce our speaker, Indranil Dev, Vice President, Product Management at Amantya Technologies. Indranil brings deep expertise in next-gen telecom platforms, 5G test automation, and AI-driven network assurance. At Amantya, he also leads product strategy for our intelligent test automation tool, AutoRAN, that's redefining how G-Node-B validation is done at scale using real devices and real-time AI-driven insights. Today, Indranil will share his perspective on where traditional RAN testing approaches fall short and how AutoRAN helps bridge the gap between lab tests and live performance. So without further ado, let me hand over the floor to Indranil. Over to you, Indranil.
Thank you, Rohina. Hello, everyone. Welcome to this session. Thank you for your time, and I hope what we talk about today is useful for you. In the next hour or so, we will talk about a paradigm shift that is happening in the RAN testing process, right? We will examine traditional processes involved in the testing of RAN and how the need for simplicity and efficiency, and of course, automation, is perpetuating this paradigm shift. Now, there are two aspects to this paradigm shift, right? The first one is characterized by the use of real devices and in the testing process. And the second aspect is the growing use of AI. We will talk about both of these aspects and how these two items can be merged together in ushering a new and exciting era of testing. Already, we have seen some use cases where application of these techniques have yielded encouraging results. But before we explore this in more detail, I'd just like to lay down the agenda. Here. Right. So the agenda for today's session, we'll start with a small introduction to the organization, Amantya Technologies. Some of you might have already attended some of our webinars and so might be familiar with who we are and what we do. However, for folks that are joining us for the first time, I think an introduction is in order. Then we will essentially divide the session into three main parts. The first part will explore the usage of real devices in the RAN testing process. The second part examines the increasing use of AI in the RAN testing process. We believe that the most significant benefits can be had by the application of AI in the field of log analysis, and that is what we explore. And finally, we understand what happens when these two come together and what benefits that would entail for the end user. We try to illustrate this with some use cases. All right, so let's get to it. So who are we? So let me take a couple of minutes to introduce Amantya Technologies. Amantya is a product engineering company. We started out in 2018 focusing on telecom technologies, more specifically focusing on the RAN and the core domains. However, as telecom domains evolved with the addition of new supplementary technologies such as AI/ML, new complementary rather technologies such as AI/ML, big data, robotics that have found significant use cases in the telecom industry, we have started to build expertise around these fields too. We are around 800 strong engineers located in various geographies across India, US, and Canada. Our customers, more than 20 in number, are characterized by a mix of operators, OEMs, and software vendors, both in the RAN and core domain, and are based in the US, UK, and the India market. Currently, we are deeply involved in serving customer bases in a host of technology areas, ranging from AI, to robotics to private networks. Our customers typically leverage our expertise in these areas to build products and access services as per their needs. We have built many proprietary products and solutions for our customers in these areas. This have also involved a few cases of customers leveraging our experiences to build research labs for different objectives ranging from AI, robotics, and the examination of open source technologies. From a product perspective, we offer testing automation frameworks. We have built test automation frameworks around the RAN and the core and Wi-Fi testing using a nuanced mix of real devices and network simulators to provide end users with the most comprehensive testing capabilities. AutoRAN, which is one of our testing automation frameworks for the RAN domain, will figure quite frequently during the course of this conversation as we go along. Should any of these items sound interesting to you, please do reach out and we would be happy to have a conversation. I think that's it about Amantya. Now let's start to get to the topic at hand. So let's start by thinking about the RAN testing in general, right? As you might already know, RAN is the most complicated part of the modern telecom network. Sometimes I wonder that this domain that has so many moving parts, it's a miracle that it works as well as it does and as consistently. However, miracle has nothing to do with it. What gets the RAN working as well as it does is a single-minded, focused approach to testing. Now, given the vastness of the domain and the different functional and non-functional aspects that need to be tested, RAN testing has traditionally been the most time-consuming and typically the most complicated. Furthermore, as with any product, the RAN also needs to undergo testing at different phases in its development, right from the start of development all the way till production. This testing is carried out by different players in the ecosystem. It follows that the objective of each of these players while testing the RAN node is different. Now there are four players that you can see in the slide here. The operator, being the closest to the end mobile user, is laser focused on end user experience. They are concerned that their RAN nodes be able to interop with the most number of mobile devices, interop well. And they are also concerned with end user complaints post rollouts. They want to keep this down to a minimum. The end-to-end RAN vendors, vertically integrated RAN vendors that make the RAN software as well as the hardware and sell the RAN node as an integrated package. They are the second party. They have a slightly different set of worries. They would like to test their end product for functional and non-functional perfection. They would also be wondering on how best their product would comply to the laid down standards of the day. They would be most interested in having scenarios, capabilities, etc. in their labs that allow them to replicate real scenarios so that they can reproduce these issues in the lab and also speed up the testing cycle itself. The RAN stack developers are the third party. So these guys typically develop RAN software. Their areas of focus would be more or less similar to the end-to-end RAN developers. More specifically, they would be trying to test software implementation, focusing on L1, L2, L3 behavior, in addition to speeding up the testing cycle. The last player, however, is a relatively new addition to this list, right? Now, they are RAN infrastructure providers. These folks have a very, very specific interest. They are a legacy of the virtualization. They're a result of the virtualization of the RAN, right? And also the fact that the RAN can now be separated into different layers as per ORAN standards. Both of these changes have allowed the RAN software to run on COTS, commercial off-the-shelf servers or the cloud. And so the COTS hardware vendors or the cloud vendors are increasingly focusing on ensuring that their hardware products or their hardware platforms provide the best platform for any RAN software to run. So this makes them a very interested party in the area of RAN testing. So you see that, while RAN testing is inherently complicated from a technical standpoint, it is rendered even more complex when you factor in the different end objectives that need to be met to get a RAN node from development to production. Needless to say, a single testing solution or approach cannot be used to meet all of these objectives. Considering the demands and the needs of the different players in the RAN testing domain, the challenges that characterize the current RAN testing ecosystem can be visualized. Chiefly, there are four. The first is, how should I ensure that my RAN node is equipped to handle the unpredictability of the plethora of real devices that it will encounter in the production field. In a real world, the RAN node will encounter real mobility, signal variations, interference, etc. From a testing standpoint, ensuring that the RAN is run through all of these items requires a different approach. The second challenge deals with the complexity of the testing scenarios themselves. RAN scenarios are inherently complex, and simulating many of these scenarios within the lab in a manner that closely mimics the real world and is simulating such scenarios at scale is very, very challenging. The third item centers around log analysis. There are cases when it is not immediately apparent from the test case behavior that the root cause of the issue lies, right? Sometimes in order to arrive at the root cause, multiple domain logs have to be manually examined over and over again before the root cause is revealed. Such a testing process is inherently inefficient and it consumes a lot of time, but is nevertheless the order of the day. Such an approach also delays testing, and eventually, there needs to be a delay in deployment of new RAN features and functionality as it turns out. The final point or the final challenge centers around the need to conduct regression testing before delivery. When new features and functionalities are released, regression testing ensures that there is no breakage in existing functionality. With every new feature, the size of the regression suite increases. Conversely, engineering teams are expected to deliver more and more feature-rich RAN solutions that is error-free in a time that ironically is consistently reducing. Surely, existing manual testing processes, they cannot prevail, and something new has to be thought of. So at Amantya, what we like to do is, we like to approach the testing strategy a little differently. Our objective, as it stands out, is real world fidelity with scale. That is how we like to look at RAN testing. In other words, provide end users with the ability to closely mimic real world scenarios within the lab, but also provide the scale that allows them to address all of their testing needs. Right now, just taking a quick look at the current practices in testing. Currently, testing uses primarily simulators that are based entirely in software or emulators that have a mix of software and hardware both. While the simulators and emulators do address many of the challenges posed by the RAN testing, the challenges that we discussed in the previous slide, our assessment, at least Amantya's assessment, is that there are still some gaps that need to be filled. The testing processes and the tools that are there, they have to evolve to fill those gaps, right? Now, simulators typically will give you a very good scripted, consistent behavior for functional and non-functional validation, but will typically not provide any real-world validation because they are not real-world. They are simulators, as the name says. Emulators, on the other hand, provides real RF validations because they are based in RF for functional and non-functional testing, but are not designed to test for the peculiarities associated with different real devices. The real devices, for example, from different OEMs or different device makers will have subtly different implementations of the stack, and those can manifest themselves in issues out in the field that are very, very hard to troubleshoot and correct. So emulators will typically not catch those. So what we feel is that while testing with simulators and emulators is important, we're not saying that simulators and emulators should be done away with. We are not proposing a replacement, but we understand the importance of the simulators and the emulators. We also feel that testing with real devices also needs to happen in a phase that just succeeds testing with emulators or simulators. So there needs to be a phase where testing with real devices also needs to happen. I believe this phase is still there, but there are a lot of inefficiencies associated with that phase that needs to be corrected. So once this phase starts to happen in a predictable, consistent, manner, only then will the testing cycle truly be complete, and we can ensure that many of the issues associated with real devices that typically should be caught in the testing cycle are actually being caught. So from Amantya's strategy point of view, it is to provide capabilities that allow the user an automated framework to test with real devices. Such a capability will also address the challenge of real-world fidelity. In addition, providing AI-assisted log analysis provides a mechanism that enables this testing to be done at scale. Let us now talk about how such a setup would look like, and when how this would change when one tries to move from a traditional testing setup to a setup that uses testing with real devices. Now, fundamentally speaking, the objective of both of these approaches is the same. Eliminate, and that objective is eliminate the maximum number of errors as early in the process as possible, right? The methodology, however, and the tools used in this approach is different, however. The current setup or the traditional setup that you would typically use these days, or the setup with our setup in the lab with simulators and or emulators, and encompassing the RAN node which is also the DUT in a typical wraparound configuration. These simulators or emulators would typically be device simulators on the one side of the RAN and network simulators on the other side. The process of testing will be either manual or would be somewhat automated. In manual testing, the user would have to set up these test cases manually and then execute them manually. In an automated setup, however, the end user would have two options. Either use the automated option provided with the different simulators independently, or run an integration exercise to control all the simulators or the emulators from an automation framework that the end user themselves have to build, right? Or get some service from a third party in order to build that automation framework for them. The log and result analysis, however, in both cases, both in the manual and the automated cases, however, remains singularly manual. Once a test case has been identified as failed, the end user typically has to manually delve into the logs to determine the root cause. As you might have guessed, and also probably experienced, such an approach is time consuming. It is error prone. It relies on the capabilities of individuals, because a person who is more experienced will probably be able to do a lot debugging a lot faster than someone who's, let's say, starting out or not so experienced. And of course, it is difficult to scale and replicate, right? Consider now how this approach can be changed when we use an automation framework, that is pre-integrated with real devices and network emulators. So such a framework or such a system, in such a system, the automation would provide the capability for the end user to write their own test cases. The test cases themselves can be organized into test suites, and those test suites can be scheduled to be executed at a predetermined date and time. The execution of the test case or the test suite itself is carried out by controlling the real devices, right? Through the automation framework, and that control can manifest itself by commands that are sent to the real devices to, let's say, initiate the test case. And there is no manual intervention that is needed for test cases to be initiated. The test case verdict itself is provided on the basis of the device and the network behavior that is as observed. Logs are captured directly from the device. New test cases can be added as new RAN features are released, and regression test cycles can be run as many times as required. Such an approach obviously enables consistent testing, consistent validation, is efficient in terms of time and resources, and of course inspires pre-deployment confidence through the use of real devices. Because chances are that many of the issues that you would typically face with real devices, but also depends on the kind of real devices that you use. The more number that you use, the better is the efficacy of the testing. But fundamentally speaking, many of the issues that you would typically encounter with real devices out in the network are caught in the lab stage itself. So as you might have also probably surmised, enabling real devices requires a different kind of approach and tool set that we talked about in the previous slide. So it would augur well for us to take a look at the different key capabilities that such a tool set would invariably need to offer. Now, to our mind, there are 5 key capabilities that such a system would have to offer. Right? The first and foremost is the ability to orchestrate real UEs at scale. Okay, there will need to be a systematic control of the UEs themselves by the framework. In addition, multiple types of UEs as per the market needs to be supported, such as Android, iOS, etc. Furthermore, there should be a mechanism to partition these UEs so that multiple users can test or use the system simultaneously. The second part of providing real network simulation relies on the ability to control the RF between the RAN and the UE. Right? For software controlled attenuators are pre-integrated into the system for simulating handovers and mobility scenarios. In order for the testing infrastructure to support end-to-end testing, simulators need to be provided to simulate network side. Such simulators could be either EPC simulators, NGC simulators, or IMS simulators. Provision of data generation using TCP, UDP, or RTP traffic also needs to be considered and provided. Capturing of logs and analysis of these logs is also another very important aspect. Capturing of these message logs from the end devices and from across different DUT interfaces, for example, the S1 AP interface or the NGAP interface is required, and also logs from different layers in the RAN node. The RRC, the NAS, L2, L1, all of these layers, are also needed to be provided. Provision of dissectors that act upon these message logs to analyze these messages and extract parameters out of these messages, and to generate PCAPs from these logs for the UE and the network side, so that the user can understand how the network message exchange or how the messages are being exchanged across the UE and the network through the DUT. That is also important for eventual log analysis. Finally, capturing of key KPIs such as the MOS score for voice calls and other similar KPIs for video, web browsing, etc., are also needed to be provided in order to conduct user experience testing, which is another important aspect. The list that I provide above, or the list that I just talked about, it's by no means exhaustive, but does provide an insight into some of the fundamental characteristics that would be expected from such a system, from a system of this kind, fundamentally speaking. So this brings us to the end of the first part, where we explored how traditional ways of testing using simulators and emulators are needed to be complemented by an automated real device testing system in order to address the challenges that are faced by the different players in this RAN ecosystem. So let us now examine the second aspect, right? The role of AI in the testing process. We feel that good gains, and I talked about this, I mentioned this before, we feel that good gains can be made by leveraging AI in the log analysis process. And that is what we will talk about in the next couple of slides. So before we get down to AI enablement of AI in log analysis, it will help us to again get some context, get a little bit of background, because as to why log analysis is so challenging, and this is not new information for many of you, I know. But just for the sake of completeness, we need to understand what are the challenges that we are looking at and how we can expect AI to take care of these challenges. It will help us in our understanding. Right. So log analysis typically has been the most time-consuming aspect of the testing process, traditionally. So many a times the system at the outset it exhibits correct behavior, right? And we see that everything is working, at least from a test case validation criteria perspective. We see that the test case is passed. But when we do log analysis, it reveals that the behavior of the system was in fact incorrect. There may have been certain conditions that fell in place, or there may have been certain race conditions that happened, which kind of led the system to behave correctly, and therefore allowed the system to pass the test case when the behavior of the system inherently was incorrect. So it obviously follows that in all cases, irrespective of the test case verdict, whether it is passing or failing, log analysis needs to be carried out. Despite the importance of this log analysis aspect of testing, it is probably the least automated because of inherent complexity and diversity of logs. You have different kinds of logs being generated by different nodes, and nodes from a particular vendor which generate logs in a particular manner. So there is a lot of diversity in the logs, and also it is difficult to it is complex to parse so many logs and deliver a verdict out of it. So the following challenges are therefore apparent that need to be addressed. So log analysis is typically manual, obviously, and inherently it is time consuming and error prone because of the inherent nature of logs and that we discussed. In order to get a complete view of the test behavior, it becomes imperative to get and correlate logs from different domains. Right, just getting logs from a particular domain and expecting to find the root cause in that particular domain is, expecting too much. That never happens. If you are in a multi-domain system, then it is possible that the issue in one domain is manifesting in an error in a separate domain. So multi-domain log analysis needs to be done, and that consequently, since multi-domains need to be analyzed more often than not, that analysis also needs manual analysis, and of course entails a delay in the overall RCA process. Furthermore, many a times this overall RCA determination is also dependent on the core capability of the individual performing the analysis. As I had pointed out, if the individual, it is very person-centric. So if the individual is very experienced with domains, with the domain where the analysis is happening, then of course the arrival of the RCA would be far quicker than the case where the individual is not all that experienced. Furthermore, this also needs a lot of collaboration between SMEs of different domains. That also is an important aspect that needs to be looked at from the overall time that is needed to arrive at the RCA. Finally, there is no real-time feedback in such a system. What this means is that even if the verdict of the test case is passed without adequate log analysis, it would be imprudent to log down the verdict of that test case as passed. For all you know, the test case might have passed due to a race condition, as I was saying, right? Or because of some unexpected behavior on the part of one of the system actors. And so, log analysis needs to be done. What this means is that even if your dashboard shows that the test case is passed, you still cannot conclude that the test case is actually behaving the way that it should without doing log analysis. So in summary, therefore, there is a pressing need to implement some mechanisms within the log analysis domain itself that can cut down the debugging cycle, render the analysis or the verdict itself agnostic to human capabilities, make this process scalable, and then facilitate an immediate and comprehensive feedback. So obviously a paradigm shift in log analysis is needed. AI-assisted log analysis seems to be able to provide an avenue to address some of these challenges, we think. So how does AI assisted log analysis work, right? And I don't want to get into the technical nitty-gritties or the technical specifics of AI, of how AI actually works, but just to provide you with a high-level understanding of how this entire AI in log analysis happens and what kind of benefit we can derive out of this. So AI models, we have AI models that are typically trained on network log data, right? And we train these models exhaustively with loads and loads of data that we generate from real testing scenarios, right? And those could have been manual testing scenarios also. Typically, the idea is to be able to train the model to identify error-free call flows against erroneous call flows. The models themselves, of course, are continuously monitored to maintain the accuracy of the processing. And as and when newer scenarios become available, the models need to be retrained in order to ensure that the capability of the model to identify these error-prone or these error-free scenarios, that keeps increasing, or the scope of identification of the model keeps growing. It's just like training a human being, right? The training of this model essentially provides the AI model with an ability to identify patterns, within logs. Such patterns are identified and then they are correlated with patterns from logs in other domains. And what this correlation does is that it leads to a far more comprehensive analysis that forms the basis of the final verdict. The implication here is that when you see a test case that shows up as passed in the dashboard, so you can kind of rest assured that this pass verdict has now been arrived at after an analysis of the individual domain logs, where pattern recognition has allowed them to identify if there have been error-free or error-prone flows, and moreover, such flows have been correlated across domains. So the verdict that has now been generated is more holistic, and it negates the need for post facto log analysis, manual log analysis. So the AI assisted approach, it is contextual as it provides the system to recognize patterns across different logs. It is holistic as it correlates logs across different domains. The approach is real time because the logs themselves are analyzed as they come up, and therefore they enable an immediate verdict, negating the need for post facto log analysis, as I just mentioned. And finally, the system itself provides the end user with a summarized and easy to understand version of the logs that essentially allows easy redressal of the problems that are faced by development teams, right? Of the problems by the development teams. So this was a primer on how AI can be leveraged, or how AI is typically leveraged to address challenges in log analysis at a very high level. Now, combination of these two aspects, the AI assisted log analysis and the usage of real devices, that also helps address some of the challenges in RAN testing with respect to automation. So combination of these two aspects entails maximum benefit for end users and also helps address the challenges in RAN testing with respect to automation, real world scenarios, scalable load and log analysis, and quick turnaround of testing cycles and stuff. So once we combine these two functions, we truly have an end-to-end cross-domain visibility, right, from a testing perspective. We completely understand what went on within the different domains while test cases were being executed. We can also rely on a verdict that is generated on the basis of protocol level exchange of messages, as to what happened during the testing. So true end-to-end visibility can be achieved. Furthermore, while real UEs bring all of their own complexities into the mix and provide a true testing environment for the RAN, AI facilitates the identification of anomalies as they happen. This renders verdict generation in real time possible, and also it renders redundant the need to sift through voluminous logs post-testing. So, you get your log, you get your verdict immediately after the test case happens, and there is no need to do any kind of post facto manual log analysis. that kind portion of that very time-consuming portion of the testing phase, that's kind of cut off. The ability to run test cases or test cycles faster, and more importantly, the ability to run the same set of test cases multiple times and be able to receive results from a consistent and predictable validation engine renders the entire testing process reliable and scalable. Clear outcomes always facilitate quick decision making, right? So if your outcomes are clear, if you know what needs to be done, then you can quickly take a call on how you need to do it, right? The test results summarized through AI can provide an actionable summary of the test result, thereby facilitating quick and accurate redressal of actions on the part of development teams. There is a if the root cause is clear, then it helps development teams to zero in on what needs to be fixed, and they can zero in on that redressal action far quicker than in the normal case, than in the traditional case. So in summary, our view is that the most benefit is derived by combining the real UEs with AI log analysis, because you see, real UEs provided real world scenarios or real world fidelity, as we call it, while AI-assisted log analysis allows us to leverage such real-world fidelity at scale. We feel that without AI-assisted log analysis, the benefits of real device usage would be limited in their impact, and vice versa. So now I'd just like to take a moment to talk about the AutoRAN. That's one of the products in our portfolio. It's an automation testing framework. It kind of encompasses many of the aspects that I touched upon during the course of the last 30-35 minutes, where we talked about real devices and AI-assisted log analysis. So AutoRAN is a tool that we've developed for wraparound RAN testing. It uses real devices on the one side. It has an automation framework, and it uses network emulators on the other side to complete the end-to-end testing setup for a RAN DUT. The devices themselves are housed in what we call device racks. You can use modems or you can use handsets, and we can scale all the way till about 256 handsets here, or 256 modems. You can also have a mix of handsets and modems depending on what your testing use cases are. On the network side, we provide emulators. So those could be NGC emulators, EPC emulators, or IMS emulators, depending on what your testing setup requires. In order to emulate or simulate real world scenarios, to test for handovers and to test for let's say mobility scenarios, we provide an attenuation assembly also. This is also pre-integrated with the automation framework. You can use the attenuation assembly under the directive of the test cases that you write in the automation framework to decrease or increase attenuation, thereby decreasing or increasing the power that is seen by the UE. And this helps us to trigger mobility or handover cases that you can test within the confines of the lab itself. From a technology standpoint, we support 4G, 5G, and O-RAN as well. There is a provision for you to be able to do parallel execution of test cases. So the entire resources that the AutoRAN system encompasses, you can divide it into different test lines, and you can have multiple test cases being executed at the same time on different test lines, thereby allowing teams to be able to use multiple teams to be able to use the same set of resources simultaneously. Smart log analysis, kind of on the lines of what we discussed in AI-assisted log analysis, is available, where anomaly detection and cross-domain correlation is done using AI models that we've developed. And also there is a visual message flow representation. So what this does is that it, as and when messages are being exchanged across the network between the DU and the DUT and the network, between the UE and the DUT and the network, a ladder diagram is also getting created simultaneously, which can give you a visual representation of what is going on in the network. It kind of helps us to understand the testing process or the test more clearly and be quick to arrive at let's say an understanding whether the test case is proceeding as per expectations or there is something wrong. So this is what the AutoRAN is, right? And now I'd just like to talk about a couple of quick case studies, right? So these are these were case studies that we had encountered during the course of testing with the AutoRAN. So the first one is, and these kind of accentuate the impact of simulated versus real UE testing, right? So the first test case was um, the validation of a VoNR call, right? And this was a scenario where we had a 5G SA setup with an IMS core and a G-Node B, and we were making VoNR calls, and the call was being, and there was handover that was happening while the call was in progress. Right. So what we observed was that while we were using simulated UEs traditionally, that we were using the simulated approach, the calls seem to happen without any problems across the boundaries of the cells, right? So we could have handovers happening smoothly. The VoNR call just continued. Nothing appeared out of the ordinary. But when we shifted to the automation or the real UE and automation setup using real devices, we found that the same scenarios elicited multiple call drops. Every time there was a handover, the call would drop. Right? Investigation revealed that there was a fallback config that required to be done in the G-Node B, which was missing, whereas the handsets, the actual real handsets, were expecting this parameter to be passed to them. The simulated handsets were not expecting this parameter to be passed to them. So the simulated handsets just continued as if nothing was wrong, whereas the handsets, the devices started to drop those calls. Now this led us to correct the configuration at the G-Node B, and we found that the handovers and the VoNR calls started to work with handovers as expected. So this kind of was a clear-cut use case or case of how simulated UEs might end up not providing information that would be helpful for real devices, or that would be helpful to be configured in the RAN in real deployments. That could lead to errors or etc. The other case was around slow throughput. Now, this was also, again, a handover case because we kind of figured that, most of the use cases that or most of the typical tricky scenarios that happen in real world situations that, deal with handovers. So we were actually investigating throughput degradation and also during handovers. So we had, again, an NSA setup here with carrier aggregation and an X2 handover. What we were doing was we were doing downloads, we were doing throughput. So we had a data generator doing down DL throughput towards the UE. Now every time there was a handover that was happening, we detected while we were doing the simulated UE part, there was no change, there was no major drop that was observed. The throughput appeared stable. But when we moved over to the real UE setup, we found that handovers were just when the handovers were happening, there was a significant drop in the throughput. The end user experience obviously was getting impacted. Analysis revealed that this was because of the fact that there was a late A3 event, a late handover trigger, or a late trigger going to the G-Node B. As a result of which, and the G-Node B also had misconfigured handover timers. As a result of which, this A3 event was not getting honored, and the handover was not happening properly, right? But in the traditional test case setup, such a thing was not apparent. Nothing really wrong was happening. The late A3 event wasn't happening, and therefore the G-Node B timers weren't misbehaving, but in an actual real scenario, late A3 events are a possibility, and they need to be catered for. So this also brought to fore one key area where simulated versus real UE testing would be important to look at. And then finally, there was another test case that we did. This was more to do with the fact that here we were using real devices in both cases. So the idea here was to be able to see how automated real UE testing fared against manual UE testing. The idea here was to detect and diagnose registration failures. So we had a similar simple SA setup with the AMF and with a 5G SA and real devices. Now, in the traditional manual real UE testing, we had real UEs manually triggered for attached loops. So multiple attached detaches happening, and we found that intermittent attach failures were happening on some devices. At least that is what we observed, right? And when we shifted to the real UE testing setup, we found that we could do this at a higher scale, at a larger scale, where a large number of UEs could be configured to do automated attach cycles via autoran quickly or at a fast pace. Now, once we got the result of this automated real UE testing, we could very easily figure out a pattern there. And we figured out that attach failures were consistently observed on specific device models. While in the traditional test case, on closer analysis, we found the behavior to be consistent. But here what should have been observed as device failures happening on identified UE models actually showed up as intermittent attach failures. And when the volume of the number of attaches increased, we found that those attaches actually followed a pattern, on specific device models. So this kind of goes to show us how important automated testing can be against manual testing. In case of manual testing, the result can be, or the implication of the test case can be right in front of you, but you may still miss it because of the fact that because of the low volume of testing, no pattern can be established, and automated testing actually allows you to establish that pattern, and that is how it helps. So this was a small primer on our understanding of real UEs versus the ability of and the capability of using AI in log analysis, and how the two can be combined to deliver real benefit for players in the RAN testing ecosystem. I'm open to take questions now. I'll hand over to Rohina for any questions.
Thanks, Indranil. That was a very insightful session. So the floor is now open for questions. Please drop them in the Q&A window, and we'll take as many as the time allows. Okay, I see we have a few questions lined up. Yeah. So Indranil, the first question that I see is, where does the lab to field gap impact operators the most? Interoperability, mobility, or user experience?
That's a good question. So, well, honestly speaking, all three are affected to some extent, but user, and it also depends on, who's asking the question. For example, in the case of an MNO, user experience is where the impact is the most profound, and it is most visible and business critical. So in lab settings, everything is controlled. Devices behave ideally. You have clean signaling, and also mobility is almost always scripted and controlled. But once you go live, you see interoperability issues crop up across different real chipsets and OS builds. Also in multi-vendor setups, when new firmware or OS versions hit the network, that is also where interoperability issues crop up quite often. So my take is that user experience is definitely something that people look at. Interoperability is a close second, and of course mobility is also important, because simulators often can't model mid-call handovers or other nuances of real world that are needed to be tested before RAN nodes can be deployed in the field. Yes, Rohina?
Yeah, sorry, I hadn't. The next question, Indranil, is, when mobility or QoE issues show up during live testing, are they typically fixed at the G node P level, or do they point to deeper device or integration problems?
So when mobility or QoE issues, so yeah, well, honestly, quite often it's a mix, right? So some issues are obviously G node V related, especially things like handover timing, bearer configurations, etc. And they are usually fixed through software patches or parameter tuning at the node level, right? But many of the issues are harder to find, and they are typically related to much deeper device or network integration problems. And those issues could be could possibly be chipset or OS specific behaviors on certain smartphones, which may manifest themselves only in real network scenarios, or unexpected app signaling or packet delays again can manifest only in real network scenarios, or integration gaps, core policy, RAN behavior. To give you an example, one operator that we worked with, they saw repeated quality of experience drops during handovers, and but only for a specific Android version with certain VoNR profile. The G B was fine, but the issue was with the chipset and the app layer interaction, and it was fixed at the device level only. We did not really have to do any changes at the at the G B level. So typically, when these kind of issues show up, there needs to be a holistic examination of the system that needs to take place to figure out where they are at. And of course, in order to do that kind of examination, specialized tools that allow users to test and recreate scenarios at in a way that the system actors would typically encounter in a real network. That kind of setup needs to be available.
Right. Indanil, the next question is, you spoke about AI-enabled log analysis. Can AutoRAN also predict degradation before it causes service disruption, or is it more reactive?
So I spoke about this briefly during the course of the presentation today. So AutoRAN basically does both, right? It supports reactive diagnostics as well as early stage predictive detection as well, right? So the AI engine that is responsible for processing the multi-layer logs or the multi-domain logs within AutoRAN, it uses real-time pattern recognition to flag anomalies as the test case is running, as the test logs are coming in. And over time, the AutoRAN will obviously learn from historical data, because that is a part of the ongoing model training exercise that we indulge in from time to time, so that the accuracy of the model, that remains top, and in order to detect recurring issues, and to flag them before they escalate into service disruptions, right? So just to give you an example, in one VoNR test cycle, a client detected a rising jitter and MOS degradation patterns in the logs, right? Well before the end user experienced any such impact. But they were able to detect that, and they were able to resolve the firmware proactively, while early firmware tuning and avoided the potential outage. So just an example to showcase that that while AI-enabled log analysis typically was designed to do log analysis for test cases, it has also now evolved to a point where we can do preemptive or predictive log analysis to avoid service disruption.
Okay, coming to the next question, is AutoRAN portable? Can it be used in field or only within a centralized test lab environment?
See, there are two variants of the AutoRAN, right? And the AutoRAN, as we see it right now, is one that was designed only for lab installations. It's one that has that can scale well. It has multiple devices. It can support racks, and it's a big system, right? However, we also understand that as networks move closer to the edge, and as teams become more distributed, operators and field engineers would need something smaller and more portable, especially when it comes to validating real world performance sites. So we built a solution that we call the Delphi. The Delphi is a smaller version of the AutoRAN. It is very compact. It's a plug and play variant of the AutoRAN. You can call it that, and it is built specifically for portability. So the Delphi again comes in two variants. It can have modems, or it can have handsets. You can take your handsets and you can plug it into the Delphi, and the handsets can be controlled by the automation framework which resides within the Delphi itself. You can do all kinds of test cases using the Delphi that you would typically expect to do with a fully blown auto-ran system. For example, VoNR testing, MOS scoring, QoE validation, full log capture is possible across NAS and GAP, RTP, and SIP layers. And there is also the possibility of the Delphi being integrated with RF attenuators to provide a real life, to provide RF control or RF attenuation control to simulate handovers and mobility test cases. While Delphi is a smaller device, we cannot really plug the attenuator within the Delphi chassis itself. So the RF attenuators are optional. If the customer wants RF attenuators to be shipped out with the Delphi system, we can integrate and ship it out.
Okay. Do operators start seeing value from AutoRAN immediately, or does it require certain scale or maturity in testing strategy first?
No, there is significant value that the operators can gain very quickly. In fact, even in early deployments, even with limited number of devices, say even 10 or 20 devices, the AutoRAN is capable of catching issues issues such as chipset quirks, call drops, or mobility handover. Example, the handover test cases that we talked about in the case study section. Those had nothing to do with volumes of test cases being run. Even a single device with the right kind of firmware, or let's say the wrong kind of firmware, or even the single device can basically catch the issues that that a simulator might not be able to detect, right? So that said, the value basically compounds with scale. As teams grow more mature, AutoRAN's automation and AI can really be more potent, especially in regression and triage. Even during pilot runs, teams often discover critical bugs related to mobility or slicing that delays rollouts, and the AutoRAN can help surface them and fix them before they go live. So whether you're a private 5G deployer or a tier one operator or even an OEM or a RAN stack vendor, there is a fast ROI that you can gain here.
Right. Indranil, there's another question. Do you have any short demo or how the testing can perform?
We have demos. In fact, we've done quite a few demos with many customers and for various functionality and features of the AutoRAN. If you're interested in a demo, you can reach out to us. We'll be happy to get into a call and show you a demo of how the system functions.
Have one more question. In scenarios where coverage is weak or conditions are suboptimal, can AutoRAN simulate these edge conditions reliably with real UEs?
Well, look, honestly speaking, with real UEs, we don't really worry about the coverage of the network per se, right? We are only concerned with the coverage or the transmission power of the DUT itself. Okay, so we are able to control the RF power between the RF power, the UECs from the RAN between the that the UECs between the RAN by use of attenuators. And yes, AutoRAN can simulate these kind of edge conditions using attenuators. We have, and these attenuators, as I said, are pre-integrated. They are software controlled digital attenuators. And because these attenuators are programmable, we can actually use them from within the test case creation interface itself. Right, so we can actually control the attenuators to set it to a particular attenuation value as per the demands of the test case to simulate cases like ping pong handovers, signal to noise ratio drops, mobility thresholds, etc. Yeah, Rohina?
Oh, sorry, I forgot to switch on my microphone. Sorry.
Yeah.
So thank you all for your questions. And I think, Indranil, we're running out of time now, and most questions have been addressed. Any remaining ones will respond offline after the session. Thank you, Indranil, for all the insights, and thank you everyone for joining us and for your questions. And like Indranil said, if you're interested in seeing how AutoRAN can fit into your testing workflow, we'd be happy to schedule a demo for you. And we hope you found the session insightful. Please feel free to reach out to us at connect@amantyatech.com or the phone number we'll be sharing with the webinar recording if you have any further questions or queries. Do stay tuned for more updates from Amantya, and we look forward to seeing you in future webinars. Thank you all.
Thank you very much.